Hello everyone. Today we will discuss amplitude modulation. It is lecture 3 for subject communication engineering KEC 401. Okay. Uh, this thing something we have discussed in last class, that is the need for modulation that requires practical length of antenna, narrow bandwidth of modulating signal, frequency multiplexing and effective power radiated by antenna by using high frequency carrier. Okay. And amplitude modulation, see there is a high frequency carrier, that is there is a signal, suppose carrier CT equals to AC cos 2 pi FCT. Suppose this is the high frequency carrier, FC is the carrier frequency and AC is carrier amplitude, and it is a sinusoidal signal we have taken. Okay. Now, this high frequency carrier in amplitude modulation, there is an modulating signal also, that is the MT. Okay. And when the amplitude of carrier signal AC, okay, it is changed as per the amplitude of the modulating signal. Okay. Then it becomes like that, a modulated signal, amplitude modulated signal, that is suppose ST, then ST becomes AC 1 plus KAMT cos 2 pi FCT. Here we can see that in place of AC it is AC 1 plus KMT. Okay. And this KAMT, basically MT is a modulating signal, okay. K is the sensitivity. Okay. So, amplitude is varying, amplitude of the carrier high frequency carrier signal varying as per the modulating signal to make it amplitude modulated. Okay. And similarly, if its frequency is changed as per the amplitude of the modulating signal, okay. If you are changing frequency of carrier, then it becomes a frequency modulation. Okay. When there is a one part, that is the phase cos 2 pi FCT plus phi, if you are changing phase value of the carrier as per the amplitude of the modulating signal, it becomes a phase modulation. These two termed as a angle modulation, and when you are changing amplitude, then it is amplitude modulation. Okay. Now, in detail we can discuss next amplitude modulation. Okay. Then once again there is a modulating signal MT and with some amplitude. Okay. It is not only not high amplitude, but low amplitude signal, high frequency carrier. Okay. It may have high frequency as well as power also may be high, and amplitude modulated waveform equation, that already in the last slides we have seen, that ST is equal to AC 1 plus MT KAMT cos 2 pi FCT KAMT. Okay. And this we can corresponding waveform can be drawn. Okay. And before going to draw its waveform, we can compare AM, FM, PM also using some waveform like that. Suppose it is a modulating signal, it is a high frequency carrier, like that. Okay. Then its amplitude modulated waveform, it is MT, it is CT, then amplitude modulated waveform ST. Okay. And here it is like this, it is a amplitude waveform. Okay, at a constant frequency. Okay. And in frequency modulation, basically frequency of the carrier can be varied as per the modulating signal. Then we are drawing here, its frequency is increasing as per the amplitude of the modulating signal, and again decreasing, increasing, and so on. Then it will be like this carrier with the constant amplitude but increasing frequency. And just a minute. Initially, just a minute, its frequency is then at the peak frequency is high, and so on. Okay. At the peak you are getting high frequency signal, and another peak again you are getting high frequency signal. In between its frequency is varying as per the amplitude of the modulating signal. Okay. And in phase modulation, this is shifted with some particular phase. Okay. And that phase also varying as per the amplitude of the modulating signal. Okay. That is also more or similar to the this frequency modulation. Okay. Now next. Okay. And this we have already discussed, amplitude modulated waveform equation, waveform we have drawn. Okay. Essential requirements for AM. Okay. And for that, basically in this equation, this mod of KAMT, this should be always less than equal to 1. It is nothing but a modulation index. It is the modulation index. Okay. Its value should be less than equal to 1, and we will plot the ST waveform for modulation index less than 1 and greater than 1 and equal to 1 in the next slides. Okay. Then there is a one requirement. Second requirement, that carrier frequency Fc should be much greater than, that is the bandwidth of the signal. Okay. These are the two main requirements. Okay. Modulation index should be less than 1 and carrier frequency Fc should be much greater than the bandwidth of the modulating signal MT. Okay. Now next, modulation index. Okay. See, modulation index, as we know that we represent it as through mu, that is nothing but the mod of KMT. Okay. In the waveform that we have drawn for ST, once again we can draw it, that is this is the ST waveform. and so on. This peak is nothing but the we can say that is the V max, this is the V min, ST was nothing but the AC 1 plus KAMT cos 2 pi FCT. Okay. Now, V max equals to basically AC plus AC Ka AM. AM is nothing but the amplitude of the modulating signal. Amplitude of the modulating signal. Okay. This is the V max we will get, and V min we will get at the lowest, that is AC minus AC Ka AM, and modulation index mu, that is the mod of KMT, that is nothing but the Ka AM. Okay. Now, we have to find the value of Ka AM through these two values V max and V min. Experimentally we can find V max and V min. Okay. Then Ka AM or modulation index mu is nothing but the V max minus V min upon V max plus V min. Okay. This is the method to calculate the modulation index experimentally. Okay. Now, illustration of amplitude modulation process. Then basically when AM waveform when modulation index less than 1, AM waveform when modulation index greater than 1. Okay. That we can see, suppose there is a modulating signal, suppose its maximum value is AM, minimum value minus AM, suppose it is going in the up to minus AM. Okay. Now, modulation AM waveform for modulation index less than 1, then it can be drawn like this. It is a middle point. Okay, that is 0. Okay. Then when modulation index is less than 1, okay, this point is going up to maximum V max, that is AC plus AC Ka AM. Okay. And Ka AM is less than 1, then AC plus AC, that is maximum 2 AC. Okay. And similarly, this point is AC minus AC Ka AM. Okay. Ka AM, that is less than 1, then AC minus AC. Okay. It may be 0, but here the magnitude of MT can be minus AM. Okay. Then these points for modulation index less than 1. Similarly, for modulation index greater than 1, then same modulating signal, okay, can be drawn like this. Then if modulation index greater than 1, it may be overlapping, okay, and it will be distorted. Okay. So that basic need, that is we will take modulation index less than 1. Okay. Now, next is the amplitude modulation, Fourier transform of the AM waveform, okay, spectrum of baseband signal, like that, that we can see ST was given as AC cos 2 pi FCT plus AC KA MT cos 2 pi FCT. If we find its Fourier transform, then suppose this is SF function of f, okay, then AC cos 2 pi FCT, we can find its Fourier transform, that is, this is nothing but the AC by 2 delta f minus FC plus delta f plus FC plus AC KA by 2 along with its magnitude also, I think. Okay. Then MT cos 2 pi FCT, that is M of f minus FC plus M of f plus FC. MF is nothing but the Fourier transform of modulating signal. Okay, Fourier transform of the modulating signal. Okay, and if we plot its frequency domain signal, then AC by 2 delta f minus FC, suppose this point is FC, this is minus FC, okay, then you are getting impulse function with amplitude AC by 2, and at this point f is equal to minus FC also, you are getting AC by 2 impulse function, and next AC k by 2 m f minus FC plus m f plus FC, then AC k a by 2, it will reduce its value, then it will be like this, like this one, okay, and this is if you are taking MF with frequency, that is the FM, then this point is FC plus FM, this point is FC minus FM. Similarly, here also at f is equal to minus FC, okay, again like that, this one, this point will be minus FC plus FM, this point is minus FC minus FM, okay. This is nothing but the as Fourier transform of ST given by this one, okay. This is the spectrum of the carrier signal, not only carrier signal but the modulating signal, okay. Spectrum of baseband signal already we have plotted, that is at frequency 0, okay. This is the MF minus FM2 plus FM, okay. That comes at the carrier frequency FC and minus FC along with the AC by 2 delta F minus FC and delta F plus FC, okay. Its amplitude is AC by 2, okay. Here this region, because we know that in this also, in the spectrum of the baseband signal, this is symmetrical to this one, okay. 0 to FM, okay, signal, its mirror image minus FM to 0, okay. Similarly, here those signal comes here, at carrier at the 0 point to up to FC, okay. Then these are two mirror image of each other, okay. And when we are showing its spectrum of the AM waveform, then its mirror image is this one, mirror image of the positive signal in the negative side. Okay. Then this part is the mirror image of this part, and it is known as lower sideband, while this part and this part is known as upper sideband. Okay. And transmission bandwidth, then in positive frequency range, this is the transmission bandwidth, Bt equals to twice of Fm. Okay. This is the bandwidth of the signal. Basically in the frequency positive frequency range, the signal around Fc, okay, and it is taking 2 Fm bandwidth. This is the transmission bandwidth around carrier frequency Fc. Okay. Limitation of amplitude modulation. See, as per the equation given of the modulated signal St, we can see in the spectrum also ki it's the power in first term, that is AC by 2 delta F minus Fc plus delta F plus Fc. It was the first term, and it is independent with the modulating signal. There is no need to transmit this signal. If you are transmit modulated signal along with this one, then it is a wasteful of the power. Okay. Similarly, AM is the wasteful of bandwidth also, because in the spectrum of the modulated signal at Fc and minus Fc, we have seen, okay, these two one are mirror image of each other, and it is the mirror image of the positive frequency range. There is no need to transmit so many mirror image of the signals. If you are transmitting only one sideband, like that upper sideband only, okay, then lower sideband can be generated at the receiver side, or another case when you are transmitting only lower sideband, not upper sideband, then upper sideband can be generated at the receiver side. Okay. Then bandwidth requirement will be only up to Fm, not 2 Fm. Then if you are taking last case of Fm, AM, then it is a wasteful of the bandwidth and wasteful of the power also. Okay. And to improve over the limitation of the amplitude modulation, what we do that we will try to transmit the signal St without AC by 2 delta F minus Fc. Okay. Then in that case, if you are transmitting both sideband, then it will be the case of the double sideband modulation, or if you are transmitting either one sideband, okay, then it will be the case of the single sideband modulation. Third case, when you are transmitting one sideband and vestige of some part of other sideband also, that will become the vestige sideband modulation, VSB. Okay. Those things we will discuss in next lectures. Okay. Thank you.